context of complex variables. Then I want to talk about the place on a cylinder, the phase pattern, and that's the thing that's most interesting initially. But then I also want to talk about the stream function, which is less familiar, but it's actually very important and very useful, because if you can calculate the stream function, you immediately know the interaction energy between two vortices, and it actually also determines the flow. And so I'm going to spend a little bit of time on that, and finally, if I have time at the end, I'll talk about the cone, which is all interesting. This was work with Niels Günther and Pietro Massignon, and we're preparing something on the behavior on a cone as well. So this is the message. The behavior on a cylinder differs greatly from a plane. And people had looked at the energy on curved surfaces, but to my knowledge, nobody's ever looked at the dynamics, which is actually very interesting. Namely, how does the vortex move on a curved surface? The phase pattern shows that the issue of single-valued wave function is non-trivial. And it turns out that in order to satisfy a single-valued wave function, the vortex has to move with a quantized speed around the circumference of the cylinder. Either plus or minus, it's a broken symmetry. The stream function gives a very intuitive picture, and I'm going to talk about that later. So, vortices are very different from particles. People tend to think of them as little particles, but they're not. They obey first-order dynamical equations, not second-order like Newton's particles. For vortices, the x and y coordinates constitute canonical variables. There's a Hamiltonian formalism. It's like x and p for a point particle. Now, on a superfluid, we typically talk about a condensate wave function with some phase phi. And Feynman said in 1955 that the superfluid velocity is proportional to the gradient of phi, and you have this constant h over m. And this is true both for helium-4 and for cold atomic Bose condensates. Now, to a first approximation, you can think of this as basically the movement of a non-viscous irrotational fluid, classical fluid, apart from singularities with quantized circulation representing the vortices. Now, in usual classical hydrodynamics, you obtain the velocity from the gradient of a velocity potential. And basically, we identify the phase of the condensate wave function apart from a constant as the velocity potential. Now, in classical hydrodynamics, there are no restrictions on the velocity potential. Because it's the phase of a quantum mechanical wave function, you also have restrictions associated with single-valuedness around various closed paths. And the interesting thing about a cylinder is you have a new additional closed path. So, another way of thinking about it, if you have, for example, a Thomas Fermi limit, is the system looks incompressible. And therefore, you can also describe it with a stream function, which is, if it's incompressible, the divergence is 0, and therefore you can use a vector potential. In this case, if it's two-dimensional, you can just take the gradient of the stream function and take the normal cross that, and that also gives you the velocity. Now, in 2 dimensions, you can use complex variables, and you can combine chi and phi as a complex function, which is an analytic function. And the Cauchy-Riemann equations give you the velocity components. And basically, what you find is that the velocity Vy plus Ivx is just the first derivative of f, which f is this function. And the stream function is important because it visualizes the flow of the particles in a very direct way. And I'm going to rely on that frequently. Now, this is basically a single vortex in a plane is just log z. And you can write that z equals r equals I phi. And if you take the first derivative, you just get 1 over z. And that, of course, with a little bit of algebra, gives you the usual circulating superfluid velocity in circles, and it's singular at the origin. And this is if you take the imaginary part, you get this color pinwheel that everybody uses as visualization. And I've added the white lines represent lines of constant phase, and the black lines are the streamlines. And you can see they're closed circles in a plane, and they form an orthogonal set because they're the real and imaginary parts of a complex variable. Now, why is chi important? Well, we'll see that it determines the interaction energy of two vortices, and it satisfies, if you look at the vorticity here, it has a two-dimensional delta function. And that if you work that through, you discover that the Laplacian of chi is a two-dimensional delta function. Therefore, chi is effectively a two-dimensional surface Green's function, which is very useful because you know in 2 dimensions, Green's functions typically have log singularities, just the same way in 3 dimensions, the Coulomb potential has a 1 over r. And chi, and I'm going to use this later, chi is completely analogous to the 2-dimensional electrostatic potential. Because if you remember, for a line charge, you get Poisson's equation. The only difference is the conventional minus sign. I use p because I've already used phi for the velocity potential. But so we know how to calculate the energy of an electrostatic field, just as the integral of E squared. Similarly, this will be the integral of V squared. And so that means a very close connection between the two systems. Now, what happens on a cylinder? Well, I'm going to let x be the coordinate around this axis and y be the vertical axis along the axis of the cylinder. And when x increases by 2 pi r, the system has to be periodic. And so you can imagine taking the cylinder, cutting it behind at the back, and flattening it out to get a strip of width 2 pi r. And it has to be periodic over 2 pi r. It's like a quantum mechanical problem with 1 dimension and periodic boundary conditions. So, how do you make vortices in this complex formalism? Well, it's very simple. If you take any function f of z, if you take the logarithm of f of z, every time f of z has a 0, the log has a vortex. And so if you want a regular array of vortices to represent these periodic repetition of a vortex, you just take the sine of z over 2r. And that has zeros equally spaced in the right places. So, and therefore you just write down what looks like the classical velocity, classical function log sine of this. Now, this is actually in Lamb's book. And it's a perfectly good classical solution. The interesting thing is it's not a quantum solution. If you look at the phase, you discover that the phase is only periodic over 4 pi, not 2 pi. And then the question is, how do you fix that? Well, this is the phase calculated from that log of the sine. And it's manifest that it's not periodic because the colors are different. You have to go 4 pi before it repeats. And nobody's ever noticed this, but it never mattered if you're just doing quantum classical physics, as far as I know. Also, the classical people didn't seem interested in the motion so much. If you take the line integral here to here, or here to here, you see you pick up a pi, because half the flux flows up and half the flux flows down. And that's unphysical. You can't imagine splitting the quantized flux into up and down. So how do you fix that? Well, you remember that the velocity is the gradient of the phase. And if you add a uniform flow, by adjusting the magnitude of the flow, you can cancel this. And so if you take this flow, IC z over r, and give c plus or minus a half, this can cancel that, and you get 0 over 2 pi, which is just what you want. And so the conclusion is, because the wave function has to be single-valued around the cylinder, the vortex must move with a velocity plus or minus h bar over 2mr along the circumference. Okay, and let me show you the pictures. You see now the picture looks right, because down here, there's no phase change, and up here you get the full 2 pi phase change. The vortex circulates in this direction, and that means the vortex here moves to the left. Here the vortex circulates like this, but it's down, so here the vortex moves to the right. And it's all very straightforward. But to my knowledge, nobody's ever asked this question on what happens on a curved surface like a cylinder. It's not clear how you build one, but it's really an interesting question, and we've spent a lot of time talking to people about that. So what is special about this plus or minus a half? Well, this is the classical piece, and this is the flow piece, but you recognize this last piece is log of e to something. And you can combine this plus this to get just log of e to the plus or minus iz over r minus 1. And that actually was suggested by Jason Ho. He said that e to the plus or minus iz are the only 2 allowed conformal transformations from a plane to a cylinder. And if you work it through, you'll see that's correct. And if you just take this flow, you actually get the same motion, which of course you have to, but now it's implicit without doing anything, adding it by hand. So, there we are. Now, let's look at the stream function. The stream function is the real part. This is the case when I've taken the vortex at rest. The streamlines are the black lines, and the important thing here is you notice that way above or way below, the streamlines are constant, so the velocity looks like it just flows to the right or to the left. For a large y, chi grows linearly, but the gradient gives you a uniform flow, which is antisymmetric. And what it says is if you take a row of vortices and you're far away, you can't resolve the individual vortices. What it looks like is what's called a vortex sheet, a discontinuity. And a discontinuity is officially unstable in classical hydrodynamics, but the vortices, at least in practice, keep it stable. But there are other very interesting features of this flow. You notice that there is a separatrix here. If you go around this region, inside this region, the flow goes around the vortex. Outside this region, the flow goes around the cylinder. So this has the same topology as the phase plot of a classical pendulum. You have the orbits like this, which are closed, and then you have the orbits that go like this or like this, and those are open. And so they're analogous to these and these, or the flow around the center. Now, if you make it move, these are the pictures you get of the stream function. And it's the same, the phase is just like what I showed before, but now you can see the lines of phase very clearly shown in white, all going up or going down. And the black lines circulate here, and otherwise they go around the cylinder. Okay. Now, the stream function is a lot more than just visualizing the flow, because it determines the velocity, and it's analogous to the electrostatic potential. For vortices in an incompressible film, the total energy is just the kinetic energy. Just the integral of v squared, where v is the sum of the velocity from vortex 1 and vortex 2, and if you take chi, the stream function from each vortex, you can write it as a linear combination. And the velocity is then just the gradient of this linear combination squared. Now, this is totally analogous to the total electrostatic potential from 2 line charges. And in the electrostatic case, you want the gradient of p squared over the system, whereas here we want the integral of grad chi squared over the system. We know from electrostatics, I'm not going to derive it, that you can use a trick, and the total energy is the same function p for the distance ri minus rj. And if it's I equals j, then you have to cut it off at some cutoff, but it gives you the interaction energy immediately without ever any more calculation. And similarly, the interaction energy of 2 vortices follows immediately from this function chi, which is very useful, and it actually has some very interesting behavior when you look at it on a cylinder. So I'll show you a little bit about that. So it's anisotropic and it's non-logarithmic for large separations, which has very interesting implications for the BKT physics. On an infinite plane, the interactions are always logarithmic. And that's the trick that's used in BKT to get the transition temperature. Here, if you take vortices far apart around the cylinder, it has to be periodic, which is non-logarithmic. But even more interesting, if you separate them in the axis direction along the cylinder, the energy increases linearly with y, and that means the vortex pairs would never break up in the ways they do in BKT physics. So we discovered people had thought about that problem 20 years ago, 30 years ago, but again, they never thought about the dynamical behavior. So now let me turn to a little bit about the cone. I got interested when I heard a talk by John Simon. He uses this very interesting non-planar configuration of 4 mirrors. And 3 of them form a plane, and then the other one is off the plane, and there's some tipping angle theta. And if you go round the details, it's a little intricate. You end up with a Berry's phase. And so if he chooses his parameters carefully, he can get a threefold degenerate solution. The details are more than I want to try to explain, but just trust me. This is from this paper, and this figure is from this paper. Here he says that the threefold symmetry is equivalent to a sector of the plane with 2 pi over 3 opening angle, because you can make 3 of them, and you go round and you see you have a figure here, the same figure here. So they all fit together. This sector and fold it into a cone. So the motion on the sector with periodicity over the 2 sides is completely equivalent to the motion on a cone. Okay? Now, he acts as if integers are very important, but actually, if you think about it, any opening angle, 2 pi over alpha, is perfectly good, because all you have to do is make it periodic over that angle, 2 pi over alpha. And that's not hard to do. If you think about the shape of the cone, the opening angle in spherical polar coordinates is sine theta is 1 over, it has to be 1 or less than 1 for physics. And so alpha is going to be bigger than 1. And that's the angle of this opening, 2 pi over alpha. So there's a direct relation between the opening angle of the sector and the shape of the cone. If alpha is equal 1, you get the full plane, and the vortex won't move because it's just planar. The moment alpha is bigger than 1, you get a slight or big angle, and there's surface curvature around. I mean, it's funny shaped like a cylinder, because in one direction the lines are constant, so the Gaussian curvature vanishes, which is the product of the 2 curvatures, but the mean curvature is non-zero. And that's true for a cylinder, and it's true for this case. So I'm just going to consider a general alpha and show you how that works. So, what is the hydrodynamic velocity for a point vortex on a film on a cone? Well, we start with a sector, 2 pi over alpha. You put a vortex somewhere inside in this angular range, and you have to ask, what is the complex potential? Well, what you need is a conformal mapping from a sector to the whole plane. And for any alpha, no matter integer or not, all you need is z to the alpha here, because you get e to the I alpha phi, and that's single valued when phi undergoes this transformation. So that's very simple. Use w as z to the alpha. Now, if you have a vortex at w0, the complex potential is just log of w minus w0. But in z log of z minus z alpha minus z0 of the alpha. And so that's a very simple function to work with. And you can do all the same numerical tricks. In particular, you can take the imaginary part, which gives you these colors on a sector. This is opening angle 2 pi over 3. But then you get the white lines are the lines of constant phase, and the black lines are the stream function. So you immediately can visualize the flow in a straight, and you see some streamlines go around the vortex, and some streamlines go around the cone, just like the cylinder. And here we've wrapped it around to make a three-dimensional cone with a vortex on it. And here we actually put an outer boundary so that there's no velocity across the boundary, and this lower circle is a streamline. But that's just added stuff. It doesn't change the physics. But it's nice that you can make these pretty drawings of what a vortex. And now the interesting question is, how does it move? Well, if you know the velocity, you have to subtract off the velocity of the vortex itself, which is a circulating flow about its position, and the difference of those is the residual that's left by the rest of the flow. And that's how the vortex moves. So formally, with this complex function, you just take the first derivative, which gives you the velocity, and subtract off the velocity of the vortex itself. So in the complex language, it's very straightforward. It's a simple expansion. And what you do, you find the vortex processes uniformly around the circumference at a particular r with a coefficient alpha minus 1. Now, it's nice that that vanishes when alpha is 1 because that's a plane, and the vortex had better be at rest. But you see, the moment you tip it just a little, there is a curvature, and it moves. It's not directly proportional to the curvature, because the actual curvature, the mean curvature, happens to go like the square root of alpha squared minus 1. And so it's not the same. And I don't understand the connection between the curvature and the flow, but this is certainly the linear translational velocity. And you have to play some games, but you can also get the precessional frequency around the cone, and it has an extra factor of alpha because it's on the sector it only moves 2 pi over alpha, but on the cone that's the whole circle. Now, R0 is the length measured along the axis, along the surface of the cylinder, the cone, but that's not really the relevant thing. The real question is how far is it from the axis? And if you say that the perpendicular direction is R0 over alpha, you get this expression. And if alpha's big, you go back to effectively the cylinder. And so if you throw this term away, that's just the answer we got for a cylinder, how it moves around the cylinder. Now, there's a very interesting question. Mathematically, what happens if alpha is less than 1? Then your sector wraps around more than once. In particular, if alpha is a half, then you get a double valuedness. The problem is that when you use this trigonometric thing, you get complex numbers. And so we've been puzzling on, if alpha is bigger than 1, the physical surface is a cone. If alpha is less than 1, is there any physical surface? And as far as we can tell, it ends up with complex, there's something called a Kähler manifold. Some of you may have studied it, and those are complex manifolds. And Bob Laughlin said, oh, I know, it's a Kähler manifold, but I don't have a really good sense of how you think about that. So it may be there's no physical solution if alpha is less than 1, but it's kind of an interesting math problem. Okay, well, that's the end, and I will just leave my conclusions, and I'm happy to answer any questions.
Yeah, thank you very much. Yeah. It's actually a quick